Q3350. What is the proper airspeed to use when flying between thermals on a cross-country flight against a headwind? A. The best lift/drag speed increased by 1/2 the estimated wind velocity. B. The minimum sink speed increased by 1/2 the estimated wind velocity. C. The best lift/drag speed decreased by 1/2 the estimated wind velocity. The correct answer is A. When flying between thermals, pilots aim to maximize their ground speed to cover the distance efficiently. By flying at the best lift/drag speed, they achieve the optimal balance between lift and drag, allowing the aircraft to maintain the highest possible speed for a given power setting. However, when flying against a headwind, the ground speed is reduced due to the opposing wind. To compensate for this, pilots increase their airspeed by 1/2 the estimated wind velocity. By doing so, they effectively increase their ground speed, counteracting the headwind component and maintaining a faster overall speed between thermals. This technique allows pilots to minimize the time spent between thermals and make progress towards their destination more efficiently. By adjusting the airspeed based on the estimated wind velocity, pilots can optimize their flight performance and maximize their chances of finding and utilizing the lift from thermals during cross-country flights. 3383. When there is a temperature inversion, you would expect to experience A. Clouds with extensive vertical development above an inversion aloft. B. Good visibility in the lower levels of the atmosphere and poor visibility above an inversion aloft. C. An increase in temperature as altitude increases. The correct answer is C. A temperature inversion refers to a situation where the temperature in the atmosphere increases with increasing altitude, contrary to the normal decrease in temperature with altitude, known as a lapse rate. Inversion layers act as a cap or barrier that prevents vertical mixing of air masses. In the presence of a temperature inversion, several characteristics can be observed. Firstly, clouds with extensive vertical development above an inversion aloft, option A, are less likely to form. This is because the stable air associated with the inversion restricts the upward movement of air and inhibits cloud formation. Secondly, visibility in the lower levels of the atmosphere is usually good, while visibility above an inversion aloft, option B, may be poorer. The stable air in the inversion layer can trap pollutants, moisture, or other particles close to the surface, leading to reduced visibility in the upper layers of the atmosphere. Lastly, an increase in temperature as altitude increases, option C, is a defining feature of a temperature inversion. The warm air aloft acts as a lid, preventing the mixing of air masses and causing a stratified layer of warmer air above cooler air near the surface. Understanding temperature inversions is important for pilots and meteorologists as they can have significant implications for weather patterns, aviation operations, and the dispersion of pollutants in the atmosphere. 3384. The most frequent type of ground or surface-based temperature inversion is that which is produced by A. Terrestrial radiation on a clear, relatively still night. B. Warm air being lifted rapidly aloft in the vicinity of mountainous terrain. C. The movement of colder air under warm air, or the movement of warm air over cold air. The correct answer is A. During clear nights, the Earth's surface loses heat through radiation, resulting in cooling of the surface layer of air in contact with the ground. This cooling process causes the air near the surface to become colder than the air above it, leading to a temperature inversion. The inversion layer acts as a cap, trapping the cooler air near the surface and preventing vertical mixing with the warmer air above. Terrestrial radiation occurs due to the Earth's surface releasing the heat it has absorbed from the sun during the day. As the ground cools at night, it emits long-wave radiation, which is a form of infrared radiation. This process is more efficient under clear skies since clouds can trap some of the outgoing radiation. The surface-based temperature inversion created by terrestrial radiation on clear nights is the most common type encountered in everyday weather conditions. It often leads to stable atmospheric conditions, reduced turbulence, and can result in fog or low-level cloud formation. Pilots and meteorologists must be aware of these temperature inversions as they can have implications for aviation operations and weather forecasting. 3397. What is meant by the term dew point? A. The temperature at which condensation and evaporation are equal. B. The temperature at which dew will always form. C. The temperature to which air must be cooled to become saturated. The correct answer is C. When air is cooled, its ability to hold moisture decreases. As the temperature drops, the air eventually reaches a point where it can no longer hold all the moisture it contains, and condensation occurs. This temperature at which condensation begins is called the dew point. At the dew point temperature, the air is saturated with water vapor, and any further cooling or addition of moisture will result in the formation of dew, fog, clouds, or other forms of precipitation. The dew point is an important measurement in meteorology and weather forecasting, as it helps determine the likelihood of fog formation, the potential for cloud development, and the possibility of precipitation. It is also used to assess the comfort level of the air in relation to humidity, as higher dew points indicate more moisture in the air and a greater potential for discomfort or heat stress. Understanding the concept of dew point is crucial for pilots, as it helps them anticipate the potential for fog, icing, or other weather hazards related to moisture in the atmosphere. 3398. The amount of water vapor which air can hold depends on the A. Dew point. B. Air temperature. C. Stability of the air. The correct answer is B. The capacity of air to hold water vapor increases with an increase in temperature and decreases with a decrease in temperature. Warmer air has a higher capacity to hold moisture, while colder air has a lower capacity. When air is saturated and can no longer hold all the moisture it contains, it reaches its maximum capacity and condensation occurs. This can happen when warm air cools, such as during nighttime cooling or when air rises and expands in the atmosphere. The relationship between temperature and moisture holding capacity is important in understanding various weather phenomena. For example, when warm and moist air encounters cooler air or experiences uplift, it can reach its saturation point, leading to cloud formation and the potential for precipitation. Pilots and meteorologists consider the relationship between temperature and moisture content when assessing weather conditions, as it helps determine the potential for cloud development, fog, or other precipitation-related phenomena. By monitoring temperature changes, they can anticipate changes in moisture levels and associated weather patterns.